Okay, hi guys, so we'll be continuing on seeing more on the endothermic and exothermic reactions. Okay, so let's say we are discussing a specific example wherein we need to identify what are the favorable conditions for the decomposition of ammonia. So we will look into that. So favorable conditions for decomposition of NH3 or ammonia. Of NH3. Okay, so the favorable conditions would be: first, removal of NH2, or rather N2, not NH2, nitrogen or hydrogen, can result in more decomposition of ammonia, because if we look at the decomposition reaction, we can see that NH3 breaks into N2 plus H2. So if we remove nitrogen or hydrogen from the product side, more of the reactant would be getting converted into products, as equilibrium would be shifting in forward direction. Second, we can have decrease in pressure. Okay, so as the pressure is decreasing, what will happen is, that delta Ng for this reaction would be negative, or I can write it that delta Ng for this reaction would be negative or less than 0. Okay, so here we can see that Kp, as Kp is number of means some constant value, as we are not changing moles of any reactant or product. So what will happen is, Kp is nothing but C times pressure to the power of delta Ng. Okay, delta Ng. So if we are decreasing the pressure, what will imply is Qp will become less than Kp. Okay, so hence equilibrium will again shift in the forward direction, resulting in more conversion of reactant into product, or more decomposition of ammonia into N2 plus H2. Third point is, we can have high temperature. So we have already discussed that this is a majority of the decomposition reactions have delta H as positive, which means energy has to be provided to the reactant in order to convert it into product. So when we are increasing temperature, in other words, we are increasing the heat or delta H in the system, hence we are facilitating the decomposition of NH3 to N2 plus H2. Fourth is, we can have addition of inert gas, okay, at constant pressure. So what will that mean? That will simply mean that if we are having constant pressure, then we know that Kp can be written as C times this is P upon total moles. So I didn't write P upon T here, because total moles in this case were not changing. But when we write something like P upon T, T is the total moles, not temperature, delta Ng. So as total moles would be increasing due to the addition of inert gas, Qp value would be getting lower than Kp value. Hence, to again maintain or reach the state of equilibrium, reactant will convert into products. So hence these 4 points will have favorable conditions for decomposition of ammonia. Similarly, you can face many problems in competitive examinations or JEE level examinations, asking you in the multiple choice question format that what all conditions will map to the given favorable condition questions. Okay, so you can just evaluate each of the following options and then pick your answer according to that. Okay, now let's discuss simultaneous equilibrium. Okay, so we'll be discussing simultaneous equilibrium. Okay, so in here we can say that when more than one equilibrium establishes simultaneously in a vessel, then a condition of simultaneous equilibrium exists or come into the picture. So when more than one equilibrium establishes simultaneously in a vessel, then simultaneous equilibrium takes place. Okay, so let's say we say that total pressure at equilibrium would be, let's say total pressure at equilibrium is suppose P. Okay, so suppose we have a reactant A dissociating or converting into product B plus 2 moles of product C, let's say. So what will happen is, so as the total pressure at equilibrium is P, then we can write that at equilibrium what might have happened, that pressure of this would be P by 3 and pressure of 2C by 3 would be 2P by 3. Only then the total pressure at equilibrium would be P, because this is a solid and we don't generally consider the partial pressure of solid in calculating the total pressure at equilibrium. Okay, so Kp in this case would be partial pressure of B multiplied with partial pressure of C squared. Partial pressure of B is P by 3, partial pressure of C squared is 2P by 3 whole squared. So we can write it as P by 3 multiplied by 4P square by 9, which is nothing but 4P cube by 27. Okay, now if we say that, for example, that total pressure at equilibrium is, let's say P1, and let's say a solid is getting converted into two gaseous products, let's say A and B. So now at equilibrium it would be at P1 by 2 pressure, and it would be at again P1 by 2 pressure, and Kp in this case would be again P of A into P of B, which would be nothing but P1 by 2 multiplied by P1 by 2, which is P1 square by 4. Okay, so now what we can say that, so simultaneously one more reaction is happening in another vessel. So let's say this was vessel 1. Okay, so we have this condition in vessel 1, and suppose we have vessel 2 as well. So this is a separate vessel. So suppose in this vessel we have Ys, which is getting converted into again Ag plus Bg. So we say that at equilibrium total pressure in this case is, pressure at equilibrium in this case would be, let's say P2. So at equilibrium what we can say that, as this is solid, the partial pressure of this solid won't be considered at equilibrium, so this would be P2 by 2 and this would be P2 by 2 also. So Kp in this case, so this is Kp1, I can write it, and Kp2 would be again P2 square by 4. So this was happening in a separate vessel. So let's see what will happen when we have the same vessel. So in same vessel, how does the conditions change here? So the original equations were Xa were converting into Ag plus Bg, okay, and Ys was converting again into Ag plus Bg. So let's say the partial pressure of, so let's say this was Cg. Okay, this was Cg rather than having Bg. Let's say this was Cg. Okay, so now what will happen is, we would have, let's say Y moles at equilibrium, we have Y moles of Cg, hence we will have Y moles of Ag as well for this reaction. And at equilibrium, what would the partial pressure, so let's say X moles here dissociated off from X solid to convert to have X moles of Bg, and it will also have X moles of rather partial pressure of, you can also equate partial pressure to the number of moles here or the partial moles here. So as they are in the same vessel, hence the partial pressure of these two gases must be equal, hence we should add X plus Y here and Y here and X here. so that as both of them are in the same vessel, total partial pressure of A would be X from first reaction and Y from second reaction. Hence we are adding Y from the second reaction in the first reaction and X from the first reaction in the second reaction. Okay, so total pressure of A would be X plus Y, for B it would be X, and C it would be Y. Okay, and we can also say that X should be less than P1 by 2 and Y would be less than, again, let's say P1 by 2. We are saying that okay, so let's forget about P1 and P2. Let's say that it should be less than P by 2, where P is the total pressure of the vessel. So total pressure of the vessel is, let's say, P. Okay, so X and Y both would be less than P by 2. Okay, so as we know that KP1 was so let me write it here, that so let's define that Kp for, let's say this was reaction 1 or reaction A. So let's say this was reaction not A and B, let's say this was reaction U and this was reaction W. Okay, so Kpu would be partial pressure of A into partial pressure of B, which would be equal to X plus Y times X. Okay, and Kp of W is partial pressure of A into partial pressure of C, which would be nothing but X plus Y upon Y. Okay, so if we divide equation 1 with equation 2, what we will be getting is partial pressure of B divided by partial pressure of C would be equal to X upon Y, which should be equal to Kpu upon Kpw. Okay, and if this is 1 divided by 2, and if we add both the equations, then we can get that X plus Y times X plus Y times Y would be equal to Kpu plus Kpw. So we can write that X plus Y squared would be equals to Kpu plus Kpw, or in other words, we can write that X plus Y, which is nothing but partial pressure of A, would be under root of Kpu plus Kpw. Okay, so if you have to calculate the partial pressure of A in the simultaneous equilibrium means two equilibriums both having some common product among them happening in the same vessel. So you have to calculate the partial pressure of that common product. You just take the under root of the Kp of both the simultaneous equations or reactions. Okay, so with this we come to the end of this lecture. We'll continue on that in the next lecture. So till then, good luck and goodbye.